Well, thank you for asking me, and it's a great pleasure to be here on this particular occasion. So, yeah, it's obvious that I've chosen this topic because it involves dialogue. There's a slight difference in emphasis between what I'm going to talk about and what's in Katerina's book, because I shall be talking about the sort of dialogue that occurs either between collaborators or just, as I say, internally within the mind of a single mathematician when one is looking for a proof. So you've got a thing you're trying to prove, you don't know whether it's true or false. And it often happens that you sort of oscillate between believing one or the other, or even if you believe very strongly that it's true, you still often sort of oscillate between trying to prove it and trying to disprove it. So one of the things I wanted to wonder, well, it's a sort of interesting thing. Why should it happen? You want to prove something to try to disprove it. Sometimes you even know it's true because you've been set it as an exercise by someone you trust or something like that. But even then, it often helps to try to disprove it. So I hoped that by the time I got here, I'd have a really clear, complete theory of why this is. What I'll actually give you is just a few sort of scattered thoughts, and I want to think of it more as a work in progress. But it's something I care about a lot because I'm engaged at the moment in a project to do with automatic theorem proving, which is becoming a bigger and bigger area at the moment because of advances in AI. Although my project is not really anything to do with machine learning and language models and things like that. It's more just old-fashioned trying to work out how we prove things and then getting a computer to do the same. I have a group in Cambridge where we're working intensively on that. So anything that sort of sheds light on how we find proofs is of interest to me. And in particular, this phenomenon is of great interest because it seems to be not just something that happens, but something that happens for very good reasons and really, really helps us find proofs in certain situations. So I'm going to start by just, I have to warn you, my expectations of you may be a little bit high because I really have to present you with some examples. And so some actual maths here. So I'm trying to keep reasonably simple. First example will be easier than the second. But I hope that even if after a while with the second example, you start getting to the point where you sort of lose the thread a little, which I think is possible, at least just getting the flavor of these internal dialogues will still be there. And I will draw some pictures to try to, so what I'm trying to do, I've sort of written some little dialogues that represent the internal dialogue. I'm going to try and sort of synchronize those with the explanations I give on the whiteboard. I've never tried anything like this before, so I just hope it will work. So here's the question I'm going to start with first. Funnily enough, although I've really often had this sort of oscillation between trying to prove something and trying to disprove something, when I actually had to come up with examples, I found it extraordinarily difficult to think of any. I don't understand this phenomenon. It's something I know happens to me a lot, but somehow if you actually press me to come up with an example. So I'm very grateful to a research student of mine, Angela Gandhi, who's one of the people working with me on this project, for coming up with this example because it actually illustrates it rather nicely. So the question is the following. You take an even number of distinct points in the plane, like sort of 28 or something like that. The question is, can you find a line that divides them exactly into two parts? So you've got to, and the line mustn't go through any of the points. So there's no question about whether it's sort of, if it's on the line, what counts. It's got to, it mustn't go through any of the points. Have exactly 14 on one side, 14 on the other, or whatever it is. You may be able to see immediately what the answer is, but let's just imagine how one of these dialogues might work. So you could say, well, okay, let's just try and find a vertical line. And then you sort of immediately realize we can't just put any old vertical line in and hope that it works. This is maybe going a little bit further than what actually would, because nobody would seriously think that any old line is going to do the job. But what would be the idea? The sort of natural idea would be you have your points, perhaps I won't draw anything just yet. You have your points scattered around. You take your vertical line and you just sort of move it across until you get sort of half the points. There will, by various mathematical reasons, there'll be a last point at which you have half under, or wait a minute, there'll be a first point at which you have at least half the points either on or to one side of the line. Just a tiny bit beyond that point, then you probably have half on one side and half on the other. So let's just see what the responses to that. So, okay, you sort of move it along, but how do you know when you go a tiny bit further that you've actually got exactly half the number of points on the other side? So the idea is when you get to sort of just that last point where you've got a half either on, you just move a tiny bit forward. You're very careful not to pick up too many more points. Surely that should work, but no, it doesn't. And here's the sort of example that shows that that approach doesn't work. So you might, this is the example suggested by Red. If I sweep a vertical line across here, when I get to the first point where I got half of the, I've got 10 points here, the first point at which I pick up 5 points, I actually accidentally pick up 6 points. So if I move a tiny bit further, I will then have 6 points to the left. But if I don't move there, I'll only have 4 points. And so we immediately identify a problem with this strategy of just picking a vertical line and sweeping it across, which is there might be more than 1 point on a vertical line. So what happens there? So let's not think too hard about this, but let's just think what was unnecessary about this strategy. And there's a very obvious thing that was unnecessary about the strategy. I didn't have to pick a vertical line. So what I could do instead is just say, well, let's hope that there's at least some slope of my line such that this problem won't arise. So one way in which we could be absolutely sure that the problem won't arise is if there are never 2 points on a line of that slope, because then you'll only pick up 1 point at a time, and then you really can go to halfway and then go a tiny bit further, and you've got half the points on one side. And but the red is getting slightly more desperate now. Yes, but there are lots of different slopes you're going to have to avoid, and then there's a final winning move. There's only finitely many slopes you have to avoid because there are only finitely many pairs of points. Infinitely many possible slopes. Done. So there's this sort of, at first it looked as though red was winning, and then by the end, black has won. Now, I think of these not as prover and skeptic exactly. It's in a way where it's slightly different from what's in the book, but more like sort of optimist and pessimist or something. Sort of one person thinks that a particular statement is true and sort of constantly saying, why don't we try this? And then the other one says, yes, but what happened? And it's a bit like that. But obviously they're close connections, isn't it? And I absolutely am not, there's any hint of a suggestion that Katerina is unaware of this sort of dialogue. It's not intended, because obviously she is. But it's just it's a slight, as I say, it's a difference in emphasis rather than a completely different phenomenon. So now here's my sort of one slide in which I'm going to try to understand why, particularly with this example in mind, why it sometimes helps to try and prove the opposite of what you're trying to prove. So one of the key facts about it, so let's suppose we start off, this PX here is a statement that we initially want to prove. And let's imagine that, sorry, the statement we want to prove, I'm imagining it's an existential statement. As in here, so actually it starts with this universal for every connection of points, but let's take that as given. Now I want to prove an existential statement. I want to prove there exists a line that has such and such a property. So I'll take the set of points as given. So I have an existential statement that I want to prove. Now what this is meant to represent is a particular way of going about it. So when you want to prove that something exists, you have to have some sort of strategy. Maybe we could build it like this. So when I say, so I'm thinking of Y as the set of sort of building blocks and phi as a function that takes those building blocks and produces an example. So in this particular case, Y might represent slopes, a set of slopes, and then phi of Y would be the first line of that slope that goes through blah, 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 plus a little bit. So this is just a sort of abstract version of what I was talking about.
What's the relationship between X and Y then?
So Y, as I say, X is the thing that you're trying to create.
Yeah.
So you're trying to find, I beg your pardon, I should have said there exists an X in capital X. I forgot to write that down. So trying to find an X in capital X with a certain property. And so what I'm saying is maybe we could find a some y, which I think of as the building blocks. I do something to those building blocks using my function phi to create something in x, and I want to prove that there is some suitable choice of building blocks such that if I do that, I'll get the object. This is a slightly stronger statement. It's saying not only is there some x, but there's some x that I can build in a particular way. And now we find actually that that's not true in general. And then there's a step where we sort of try to identify as well as possible the reason that this statement failed. So we want to say not only is there some y that doesn't, such that phi of y doesn't have the desired property, but any y with property q, for some property q, fails to have the property that we wanted. And then having done that, we could say, well, okay, we know that y's such that q of y holds are problematic. So let's just try to avoid those. Let's try to prove the following two statements. We'll try and prove that there is some y that doesn't have this problematic feature, and that every y that doesn't have this problematic feature works. Again, this is a sort of scheme of what we just did with this problem over here. And sometimes not q. So not to q in the case of this line problem was slightly complicated. It's sort of the line where you first reach half the point and so on. And it turned out to be easier just to say perhaps we can find a line that never contains more than one point. So it's we've sort of generalized it to a more convenient thing. And we've ended up with this as our new sort of strategy for proving things. We'll try and find a y that has this nice property r, and r implies p of this. Now, what have we gained from doing all that? Well, when you're trying to prove something, you don't know how to do so. Very often you want to find some intermediate statement. And sometimes when you've got the right intermediate statement, it's very easy to go from here to here, from here to here. But finding that intermediate statement is the problem. So from a logical point of view, you've done nothing at all. But from a sort of proof finding point of view, it's a very somehow different perspective. Something very important has happened here, which is we've identified a really good intermediate statement. Can we find a slope such that no line with that slope contains more than one of the points? Once you've got that, if I tell you as a clue with the original problem, hint, first find a slope that doesn't contain more than one. Maybe we can never find 2 points connected by a line of that slope, and then proceed from there. Well, that would make the problem much easier. So that's why. So from a logical point of view, for example, trying to prove the opposite of what you're really trying to prove would seem senseless. And other things seem senseless, like sometimes it's helpful, if you're trying to prove a statement P, it's helpful to start by trying to prove a statement that's a consequence of P. So you might think proving a stronger statement than P will be useful to you, but proving a weaker statement than P, that's pointless somehow. But it's not pointless because a weaker statement than P has a negation that's stronger than the negation of P. And if you sort of turn around and try to prove the negation, then that is a sensible thing to do. So there are various sort of seeming puzzles that make sense if you think about everything from the perspective of finding proofs, but not so much from the perspective of just checking the correctness of proofs. Okay, so I would move swiftly on. So this is just something to bear in mind, in the back of your mind. So I'm going to move swiftly on to a significantly harder problem, which I think I shall just need to explain a little bit of terminology. So if you've got a set of real numbers, we can just think of those as points on the number line. It's called closed if whenever you have a point that's not in the set, you can find a little neighborhood of other points, so a little sort of interval around that point that doesn't intersect the set. Or another way of saying it, actually, which is perhaps better from what I'm about to talk about, is closed. If whenever you have a sequence that converges to some limit like that, the limit also has to belong to the set. That's why we call it closed. It's sort of closed under the process of taking limits. If you're not, if you've got a bit rusty on what convergent sequences are, they're just basically things that look like this as we get closer and closer to some point. So, for example, the sequence of half, a third, a quarter, a fifth, a sixth, and so on, that converges to 0. It's sort of getting closer.
What about infinity? Converges to infinity? Surely that's like.
That will. It's possible to make good sense of tending to infinity.
Okay.
But from this here, I'm not going to count that. So what you can do is you can sort of add a point to infinity. That's all, you can make mathematical sense of it, but I'm not, that's outside what I'm doing right here. So everything will just live inside some bounded region, if you like. And an isolated point is what it sounds like. So it's just a point where you can find a little interval. Well, I've drawn a different picture here. But if I've got a point in the set, I call it isolated. If I can find a little neighborhood at that point with an interval around it that contains no other points in the set. And countable, if you've read about Cantor's diagonal and things like that, you'll know about this. So countable just means I can put the elements in some order, sort of. Like I said, that's the first one, that's the second one, that's the third one, that's the fourth one. And I run through and I'll run through all the elements. And famously, the real numbers themselves are not countable. All you'll need to know really to follow this, perhaps I won't even say it until we get there actually. So this is the question: can we find a non-empty, countable, closed set of real numbers with no isolated points? There are a few, these are called perfect sets in that. So let's just start and take the screen over here. I'm not going to read out this dialogue. This is a bit where I'm going to try to synchronize my explanation with the dialogue to some extent. It's sort of hypothetical dialogue. Again, I'll exaggerate, I think, the extent to which one really does flip from one direction to the other. So optimist here is saying, yes, I think there is such a set. Pessimist is saying, I think there is no such set. So the pessimist is going to sort of, I put this in red because it's a restriction on what the sets can look like. So it's sort of bad news for the person building a set. In fact, it is bad news because if the set was allowed to be non-empty, then it'd be done straight away. Oh, sorry, if it was allowed to be empty, you could just take the empty set and it would satisfy the conditions. So we start with a point. That's the response. Okay, we have to take a point. Fine, let's take a point. Now, that point is not isolated, so we've got to do something about that. We've got to make sure there's no neighborhood around that point. But what we do about it is we create some sequence of points that converges to that point. I could have had some points coming in the other side as well, but that's not so important. Now, every neighborhood I put around that point will contain not just one, but infinitely many of those points. So dealt with that problem. Or have we? So that was even the problem. So my synchronization is not perfect. Have we dealt with the problem? Well, the point X is dealt with, but we've just created a whole host of other problems. All these points are now isolated. So let's just call them X1, X2, X3, X4, and so on. Each of those are isolated. So do we go off and cry somewhere? Well, don't give up straight away. We can just sort of de-isolate those points in exactly the same way. So let's do that. That's like the end of COVID restrictions, isn't it? So we have to find notation. So we call this X11, X12, and so on. It gets more and more unpleasant as you go on. X21, etc. X31, X32, so forth. You can see where this is going. So actually, there's something that with this picture I overlooked, which is can't just take any of the sequences X1, X2, X so on. Because I could have done something very stupid, which was to have my X here, have my initial sequence. What if I had, so let's say the real number line carries on over here somewhere. What if my X11 was this point, and my X21 was this point, and my X31 was this point, and my X41 was this point, and my X51. And I ended up with all the rational numbers in this interval, just by taking on the first numbers in these sequences. Then the limit points of those rationals would be the entire interval, and the entire interval is uncountable. And then I would have had uncountably many limit points, all of which I would have to put in. And I'd be that would be the end of this attempt. However, you can see from the way I've drawn it, I can actually make sure that won't happen just by putting all these xi's in little sort of, well, enclosing them in intervals like this, and just promising that my sequences will live inside those closed intervals and keep apart from each other, so they won't do anything silly like this. Fine. And so this process is just going to carry on and on and on. So I've got to, yeah. There we go. So I will stop trying to draw that because it's going to get really unpleasant. But you get a sort of general idea. I sort of blow this, I zoom in on this with a microscope, and then I can put little sequences tending to these ones. First of all, I surround each of these by even smaller intervals. I'm calling this interval x1 minus delta 1 up to x1 plus delta 1. And then I'll have things like later on in the process, I might have x 5418 minus delta 5418 up to x 5418 plus delta 5418 and so on. Okay. And well, I've got rather a lot of things that I'm doing, a lot of things I'm adding, so I've got to be a bit careful about that. Actually, this is not a problem because so this is one of the small bits of theory that one needs to know about countability. Each of these sequences is a countable set. At each stage, I add only countably many sequences. If you add countably many countable sets, you're only adding countably many things and only countably many stages, and so you're doing countably many times, blah, blah, blah. So at the end of that countable number of stages, you've got a countable set. So it's all looking really quite promising. But red has not given up yet. Sorry. So it is countable, but is it closed? Let's just think about what happens at each individual stage. So at the first stage, this is clearly closed, but any set that's not in here, any point that's not in here, you can see there's got an interval around it. This is this point. At the second stage, that's also true because, again, if you take a point that's not in the set, either it lives inside one of these little intervals or to the left of this, and then again, in both cases, if I hadn't got this original x, then there would have been a problem because I'd have a limit point that wasn't in the set. But at each individual stage of this process, it's actually quite easy to check that the set is closed. But unfortunately, a union of closed sets, or sort of union of infinitely many closed sets, doesn't always have to be closed. That's another simple fact from maths. So we actually can sort of see that. If you take the rationals one after another, at each finite stage, you've only got finitely many points, and so it's closed, but the rationals themselves certainly don't form a closed set. So it's not completely obvious. And now somehow things are going to switch, and red is going to sort of become the one who sort of suggests things, and black is going to, but red's suggesting something that's going in a negative direction. So red's going to try to find a sequence that converges. Now, one of the key things that, one of the key points I haven't made stressed yet enough is when you're trying to find a counterexample while you're playing this game, it's much more helpful if you try to find as general a counterexample as possible, because then if it fails, you learn more. If you just try and find a very specific counterexample and it fails, well, you just know that that specific counterexample failed. Although sometimes also you find a very specific one, and after it fails, you then try to generalize and sort of say that actually it only needed these properties to show that it failed or something like that. So, but anyway, so that's why red doesn't want to just immediately choose the first term of this hoped for non-convergent sequence. So things that sort of tables are turned back. Actually, no, they keep turning. I think I took this by myself. All right.
They're both persistent.
I can't answer for them, but let's just stick with what red has said here. So red is going to try to find all sequences that converge for something that's in the set, and then argue that there must be other sequences that converge that are not included in that. So I think I'm a slight sort of, I want to hurry a little bit. So let's think about sequences that tend to X. That's what, yeah. So we've got the one that we first built, X1, X2, X3, X4 tends to X. We can see actually there are lots of other sequences that tend to X. So red is a little bit optimistic that that would be the only one that, but we could have taken sort of some other point here and another point here and another point here and another point here. But what we see is if we want to get things to converge to X, they're going to have to get in at least into intervals that get closer and closer to X. So the sort of the numbers of the intervals that we choose have to get higher and higher. I haven't, so this interval IN is the sort of, this is I1 here, I2, I3, I4. So we have to belong to the intervals with higher and higher indices. That's what I'm saying here. And you can fairly easily verify that the converse is true. If it does converge, then it has to belong to those intervals. If it belongs to intervals with higher and higher indices, it converges to X. Conversely, if it converges to X, it has to belong to intervals with higher and higher indices. And then we can generalize as a little bit of a false step that red takes, but I think we can pass over that and just say, if you want to get something that converges, let's say to X3, then at some point you have to end up in I3, and then you're in the same sort of position where you'll be in I, you've got the intervals I31, I32, I33, that's one surrounding this point, and so on. And then the second index has to get bigger and bigger if you want to converge to X3. And in general, if you want to converge to some point X I1 up to IK, then eventually the behavior you have to have is that it's got to belong to the interval I1, IK, R, but R getting larger and larger and larger. So I will just, what was the talk about that one ago? Yes, so having established what these sequences that converge to points in the set must look like, black suddenly says, right, maybe they're all like that. So maybe maybe it'll always be the case that you sort of, if the sequence converges, it eventually settles down to being I1 up to IK, in the interval I1 up to IK, comma R, where R is going up to infinity, something like that. And then a little bit of a discussion takes place. Maybe I recommend maybe not trying to think about this too much, because the notation gets really unpleasant if you have a set of indices at the mth stage. So I have to have a sort of suffix, a superscript m as well as the subscripts 1 up to k, and k can depend on m and so on. But let's just jump to the main point, which is after a bit of discussion, the black is still very optimistic at this point, but then red comes up with the killer example, which is, what about if the sequence does sort of settle down with particular indices, but gets longer and longer? So what about something like, so let's just have a look over here. What happens to X1, then X11? It'll be this point here, and X111 will be another point a bit closer to, if you think about that, it doesn't converge to X1, it doesn't converge to X11, it doesn't converge to X111. Those are the only things it could conceivably converge to. It doesn't converge to any of them, so it must converge to something new. So, but that's just one counterexample, so we could have just added that one in. But it's not just one counterexample, because we can obviously play the same game with any infinite sequence of natural numbers, and one can check that those all tend to, those all give us sequences that tend to different limits. There are uncountably, this is the other thing you need to know about countable sets, there are uncountably many sequences of natural numbers. So we've got actually uncountably many limit points from this construction. So black is not, haven't quite given up at this point. Sort of dries his eyes and says this, I just tried to produce one example and that failed, but who knows, there may be another example. But that doesn't become much ice because of this phenomenon I was talking about, where we just didn't want to specify too much. I didn't tell you what X was, I didn't tell you precisely what the sequence was that converged to X, and so on. And because I didn't tell you very much, it turns out that you can build this example basically inside any perfect set. So here red is just saying, ha ha ha, you've told me how to win this game, because if I've got a closed countable or a closed set with no isolated points and it's not empty, of course I can find an initial point. That point's not isolated, so I can find a sequence that converges to it. Those points aren't isolated, so I can find sequences that converge to them. Those points aren't isolated, etc., etc., etc. And you can just check this whole thing takes place. So in some funny way, I've even got a colleague who said there's no difference between trying to prove something and disprove something. This is a rather extreme example of that. The whole attempt to find an example turned out to be extremely helpful because the attempt was sufficiently general to prove that there's no example. And that may be everything I was going to, yes, it was actually. So I've got through what I wanted to talk about in half an hour. Right, okay, I'll stop.
Thank you.